Uh, we've been talking about root locus, what it is, and how to sketch a root locus by hand. Um, and what it is where are the roots or the poles of the closed loop system as a certain parameter k goes from 0 to infinity. And they always start at these little x's, which are the poles of a certain function L of s. So these lines here, these colored lines, say where the closed loop poles are as you vary k. So how do you figure out what k gets you to a certain point on the root locus? Like what k would get us to this point? That's what I'll talk about in this video. Okay. To get there, we got to talk about a little bit of complex number review. And you might be used to a complex number z is a x plus a jy, where x and y are real. Think about it in the complex plane. We've talked about this before. Here's the point in the complex plane. You could also think of it in polar coordinates. It has this distance or magnitude from the origin and this angle, horizontal, angle up from the horizontal right. So the magnitude of z with these absolute value looking signs, that means the magnitude of a complex number. You just use Pythagorean theorem to find that from the x and y. And you could express that complex number this way. What is x? It's the magnitude of z times the cosine of theta, and y is the magnitude of z times the sine of theta. Well, you factor out the common factor of z, and you're left with something that turns into e to the j theta by Euler's theorem. Anyway, so here's the other way to express a complex number. Here it is in rectangular coordinates. Here it is basically in polar coordinates or in phasor form. What I want to get to here, what if you have a product of two complex numbers? What is the magnitude of the product? Well, it turns out to be the product of the magnitudes. And we're going to use that in a minute. And the angles, if you look at how you express it in phasor notation, the angles add. When you multiply two complex numbers, their angles add. Their magnitudes multiply, their angles add. And if you divide them, the magnitudes divide and the angles subtract. So with that, remember with root locus, we manipulated the characteristic equation into this form. Some L of s, a lot of times that was your g times your h, not always, depended on your parameter of interest. We've covered all that in previous videos. But if you take this, where L of s is a complex number in general, so L of s is a complex number. This means L of s equals minus 1 over k. K is a real number greater than 0. So the magnitude of L is 1 over k. The angle of L is 180 degrees. That means L is something like this. The magnitude of that something can be calculated this way because of what we just covered. The magnitude, you can take the magnitude of the numerator divided by the magnitude of the denominator. But each one is just the product of the individual magnitudes of each term. So this overall magnitude can be calculated this way. That equals 1 over k, whatever k you're looking for, this k sub 0, which just means a particular k. So we can calculate k sub 0 this way. We turn the L upside down and put the point we're interested in from everywhere there's an S in L. And that's how we calculate k sub 0. And by the way, the angles have to do this, numerator minus denominator. and they add and they add. And this is where we got rule 4 from when we did sketching by hand. Let's get into an example of how to calculate the K. So here's our L. Here was the root locus, and we're interested in this exact point where it starts splitting off. And we already calculated that as -4 plus the square root of 3 in this case. So what do? Here was L, turn it upside down, and replace every S with -4 plus the square root of 3. -4 plus the square root of 3 plus 1, -4 plus the square root of 3 plus 3, and then on the bottom all the same, plus 4. These are all real numbers here, so the magnitudes are simply truly absolute values, and you end up with this, which is approximately that number. Nothing complex in that case. There was no complex arithmetic in that case. What about this point up here, directly above the center of the circle? That corresponds to -4 plus j square root of 3. That's the coordinate. That's the location at this point. So again, we turn the L upside down and replace S, every S in it, with -4 plus j square root of 3. So bottom becomes the top, the +1 and the +3. The top becomes the bottom of +4. Combine the real parts and the imaginary parts for each thing you're taking a magnitude of. So here you have a -4 plus 1. It's a -3. The imaginary part still a j square root of 3. Here you have a -4 plus 3 again. Or no, -4 plus 3, which is -1, plus the j square root of 3. And similarly, here the -4 cancels the 4, and it's just j square root of 3. How do you find this magnitude? Pythagorean theorem. It's going to be 3 squared plus the square root of 3 squared. 3 squared plus the square root of 3 squared. And then the square root of that whole thing. Anyway, you do all that arithmetic, you end up with the number 4. So K start out at 0 here at this X, and at this X, here it was, what did we say? A little over 5, 0.5. Here it's 0.5. And as K increases, it gets to 4, and that's when it's up here. So you could compute any K on the root locus that way. Okay, that's enough for K. Our next subject will be designing controllers. And I'll leave that for next time. Next video.